Okay, and let's go from current slide. But before we get going on today's slides, let me review just a couple things. Number one, obviously, Screencast-O-Matic is working again. So hopefully it'll load. The first class didn't load, but hopefully the second and first will load now. And next, what you do if you do want to review material that we did last time, but I couldn't record it. Well, here's how I do. It's sort of bizarre, but what just happened is the reason I do it. When I start a new term, I don't wipe out the old term. I'll leave it in there, okay? So that if you've been going to YouTube videos, I hope you've noticed this, the ones at the top are things we haven't done yet. Those are ones from last term. The ones at the bottom are the ones we're doing now, and they load at the bottom. And of course, Tuesday there wasn't anything to load, but we did do material. So, let me back up. So when I do a class and I load it at the bottom, I go back to the top, and if it duplicates something we did last term, I remove the old one. Okay. So what we did last time, certainly there's nothing to put in, so I won't eradicate or erase or delete that one at the top. Okay. In fact, there may be two up there. I don't know, because you see in the actually, we should be okay. Okay. Because in the regular term, I teach this on mini terms, which are only 8-week terms, so they're even longer. And so there's probably more covered in a class then than is covered now. So I think we'll be all right. The thing is, there may be a gap that we miss on, and there's got to be some overlap. So you'll be able to figure it out. But the one we missed, I'll try to leave at the top. And it may actually, because the overlap doesn't coincide well, I may have to leave two. But my guess is I'll just leave one up there. And you'll be able to follow. But they'll be out of order, sort of. And it'll be a different class. So anyway, that's how you'll be able to follow on Screencast-O-Matic or YouTube video approximately what we did. The same subject material, but it may be off a little bit on start and end times. Okay, now let's do a quick review where we are and what we've done. Oh, let me say this too. I have called several times to the planetarium, finally got the gal that I talked with the first time. Never have been able to talk with Mr. Weigel because sounds like he's just busy this summer. And that follows what I was about to say. When I finally talked to the gal that I talked with the first time, and she said, well, we're stacked all summer long, but if he's going to be gone the week of the 4th of July, we might be able to squeeze you in then. Well, when I talked with her this time, she said, yeah, I talked with Mr. Weigel, and he didn't think it was a good idea to have, because they're just students too. He said, students teaching students. I said, look, my students aren't going to object because it's always a good show, but I said, I'm not going to argue with them. He said, and she said, well, the other thing is, it's a brand new system they've just installed, and they don't feel, I don't think, completely confident trying to run it on their own without him being there. So she said, nope, she said, we are stacked completely except the 4th of July week. Everything is occupied, so can't do it. But she did give this as an option. And you can remember this forever. Every Thursday evening at 8 o'clock, they have a special show at the planetarium at Sanford. I think she said 8 o'clock. Check out on the website. I'm sure it's there. It's the Christenberry Planetarium at Sanford University. I think she said every Thursday at 8. And she said, encourage your students to come to that. I said, well, how can I document that? She said, well, we can send you our roll sheets. Well, I'd have to get roll sheets. I said, are they very well attended? Oh, yeah, there's plenty of people here. I said, so I'll have to check all your roll sheets from now till the end of the term and make sure I don't miss a name in it, because there's going to be lots of names. I said, is there any way that they can get something and bring back to me me. She said, oh, that's a good idea. She said, I think we can do something like that. So I'll put it this way to you, just in case they forget to or don't do it. Why don't you carry something with you? If you want me to come up, but you can just take a piece of paper. This is to certify, indicate, guarantee, or whatever that blah, blah, blah has been there, and ask them to sign it. You bring it back to me, have the date that you went, and stuff. And if you go to it one Thursday night before the end of the term, bring that form to me that they've indicated you were there, and I'll give you credit for 25 points for the lab. Okay. Yeah. And I knew that was going to be the case for some people. So it's optional. It's completely optional. Okay? As was the whole trip was going to be optional. I can't force someone to go to the planetarium. So what I did, and this will be the same for the Weather Center, it'll be a lab that is optional, but if you go, you get 25 points for the, okay, you get 25 points just for going, and then you can drop a low lab if you wanted to. You already get to drop one, but this enables you to drop the second, and the Weather Center will drop the third one if you needed to. Most of you aren't going to need to, but in case you wanted to. And then if you can't go, you just can't go. So. Huh? Yeah, and you're bringing something back. Okay? But, again, it's completely optional. Y'all are doing well in your lab. None of you are going to need it. But, it's there if you want to do it. And it's a fun show. I've not been to the Thursday nights, but everyone I've been to there has been really, really good. And Mr. White will be there. Now, they will not have one the week of the 4th of July. That's the 5th of July, that Thursday night. He'll be out of town, so they won't do it. But he runs the show on Thursday nights. So. What's that? Am I going to have class what? Yes. School is open. Okay. It's bad news when it's in the middle of the week like that, but yeah, we'll be here. Always. Okay. Unless something really major happens that I don't want it to happen, yeah, we have classes then. I have classes on Tuesday and Thursday. 4th of July is the only day we get off. Okay, good questions. Oh, yeah. So, where are we today? Where have we been? What are we doing? Like I told you when I just returned papers. I returned lab 1 and test 1. Lab 2, I'm missing 1, so as soon as I get it, I'll be able to return that to you. Test 2, I just gave you back. Lab 3, you're working on. And test 3 we'll have next Tuesday. Tuesday, the last 30 minutes, the test on this chapter we're on now, 17. Okay? Shouldn't have said that. Okay. We had test 3 already. I left off that. We had test 3, but like I said, 3 people haven't done test 3, so I have to wait till they do it, get it done. So that's test 3. Lab 4 we'll do today. The last 2 hours today we'll do lab 4. We're going to do it down in the orientation classroom, room 256. I've checked it several times a day. It's unlocked, and so far no one's been in there all day. They weren't there on Tuesday either. However, Tuesday it was locked, okay? And so I'm hoping no one shows up this afternoon and takes it over. But I think it's free today. So the lab will be the last 2 hours a day. That's from 1:30 to 3:30, okay? It won't take you that long, I don't think. So you should be able to be through. Now, because we're going to finish the chapter, if I finally get around to teaching, today, we'll finish this. And that means the test for this chapter, the test 4, the chapter 17 test, will be the last 30 minutes on Tuesday. Okay? Now, we'll finish chapter 17 today and probably get started in 18. All right. Any questions? That's where we've been, where we are, and where we're heading. Okay. Okay. So far in chapter 17, we first talked about minerals. Minerals are the things that make up just about everything. Most of the solid material is inorganic solid material, not the trees and wood and things like that. Inorganic solid material is made up of minerals. Okay? Now, minerals are well organized crystal structures, non-organic, not lit directly from living things, those kind of things. They're generally fairly pure. You can have some impurities in them, but generally fairly pure. Great crystal structure, that kind of stuff. Now, then we move to rocks. Rocks are aggregations of minerals and other stuff, okay? The other stuff is interesting. And there are three basic types of rock. What are they? We talked about the first two already. Okay, metamorphic is the third one. What's the other one you said? Sedimentary? Yeah. Okay, that's number two. What's number one? Igneous, got it. Okay, igneous, sedimentary, and metamorphic. Now, igneous has several ways to classify it. One is by grain size. If it formed, okay, igneous comes from molten materials. Okay, hot, ignite, hot materials, molten rock, volcanic. Even if it didn't come to the surface, it came from magma. Okay? Now, if that cooled slowly, which most of the time is inside the earth, cooling slowly, that usually made big, coarse crystals. Okay? That's called intrusive igneous rock. If the magma made its way to the surface and became lava and cooled rapidly, that made small crystal sizes, and that's called extrusive igneous rock. Okay? So that's one way to classify igneous rock, by crystal size, which has to do with the rate of cooling of that magma. Other ways is whether it had whether it's a silicate or a non-silicate. 92% of the rocks on the surface of the earth are silicates. 92%. Only 8% are non-silicates, and we looked at those too. Okay? Now, the silicates are either ferromagnesium, meaning high iron content, non-ferromagnesium, meaning low iron content, or clay. Okay, those are the types of silicates. Okay. Kayla is here. All right. Now, and Guy is here, right? Yeah. You weren't here Tuesday at all, was it? Okay. I had accidentally put a P there. I said, I don't remember that he ever came in, and you didn't take the test, so I thought, I don't think he did. Didn't want to change it until I verified it with you. All right. Let me just, sorry about the backup here, but about the visit to the planetarium, we had talked about that before. We cannot go as a class. They are booked all summer long. They said possibly the week of the 4th of July, when Mr. Weichel was going to be out of town, we might be able to squeeze in there. But when the student worker talked with him, he said, nope. Evidently, a lot of the equipment they have is brand new, and he doesn't want to risk having the students trying to run the equipment without him being there. And so, but what they did suggest, and what you can do, if you want to try to get those 25 points for that optional lab, is every Thursday evening at 8 o'clock on the Sanford campus, It's the Christenberry Planetarium. They're on Sanford's campus. They have a show, free show to the public. And usually it's fairly well attended, so I would not be late getting there. I think there'll be room, but if you want a good seat. And those are really good. And what you do, and I suggest, she said, the student I was talking with said they would try to do something, but just in case they forget to, I would take with me a piece of paper saying, and put your name on it, saying this is to certify, verify probably that your name attended on this night, and have them sign it and bring it back to me. I'll give you 25 points for that optional lab. It's optional. You don't have to do it, but if you want to go see it, it's well worth the effort. Okay? So, we won't have that. And then the other thing is today's lab, the Chapter 17 lab, will do the last 2 hours a day, starting at 1:30, which means I need to get a move on. Okay? All right. So, we were talking about the types of rocks. We talked about igneous rock that are either, and we talked about grain size, coarse grained or fine grained, depending on the cooling rate of that magma. And then we were talking about whether they're silicates or non-silicates. Then among the silicates, we had ferromagnesium silicates, high iron content, non-ferromagnesium silicates, low iron content, and the clays. Okay, those are all silicates. Now, then we talked about the 8 classes of non-silicates. So that pretty much beat to death igneous rock. And then we went to sedimentary rock. Sedimentary rocks are pieces or parts of other rock that have broken down or dissolved or something and then reformed to new rock. And that's what makes sedimentary rock. 2 types of sedimentary rocks based on where they came from. Anyone remember those 2 types? They're both C words, by the way. One came from particles of other rocks, sandstone, breccia, conglomerate, those kind of things. Those are clastic, not classic, but clastic sedimentary rock. The other is chemical, the other C word, chemical. And those are once they dissolve and then reform to be other rock. Okay? Those are your 2 types of sedimentary rock. And that reforming, especially of the clastic rock made out of particles, that the 2 processes there is compaction, which squeezes the pore spaces down, probably squeezes out most of the water, and then cementation, where the remains of things that were dissolved in the water stick the other particles together. So that's your 2 types of forming sedimentary rock. First compaction, then cementation. Then we move to metamorphic rock. Okay, I think that's where we're starting today. We haven't done anything on this yet. So this is on page 450 if you're following in your book. And what are metamorphic rock? Does anyone know what metamorphosis is? What that means? Metamorphic. Sorry. Second? Change. Excellent. Very good. Change. Metamorphosis. I don't know if any of you follow Scripture very much, but one of the most, in Romans, 2 of the really pretty well-known verses, don't be conformed to the dealings of the world, but be transformed by taking on the new identity, that type of thing. That means that's metamorphic. Okay? Probably the place where most of you have run into it, say in biology class, would be the caterpillar. That process of becoming, going into a cocoon and coming out a butterfly or a moth. Okay? That is metamorphosis. Way big changes, right? Now there was one other example of this, and I'm not even sure I can remember the author's name. He's really famous. Right now I'm going blank on it. He was one of these weird German writers. I know him. I cannot think of his name right now. He wrote about the same time as Thomas Mann, but it wasn't Mann, I don't think. It was the other guy. He's much better known, I think, than Mann, but I cannot remember his name. But he wrote a book, and the name of the book is Metamorphosis. And the premise of the book, rather strange. This one guy was really, I think, fairly obnoxious, always complaining, griping, not satisfied with anything. He woke up one morning and he was a cockroach. Okay, and that was his metamorphosis. And then he got to see what life was really like in the pits, you might say. So anyway, those are all forms of metamorphosis. These are rocks that have been changed and changed big time. They were previously existing rocks, and they were already rock. Now, sedimentary rocks are previously existing rock, but they've worn away. They've broken into pieces. They've dissolved. They've whatever, and then reformed. That's not the same here. These are actual rocks. They stayed rocks, but now they're changed, metamorphosized, changed by these three major situations, and two of them are very similar. Heat, pressure, and then hot solutions, okay? That's, again, heat, but now you've got some dissolution going on there, and it's changing that way. Now, picture this, okay? A rock gets buried, remember, like sedimentary, and just keeps getting buried and pushed further and further down into the Earth's surface. Now, two things are happening there. One, more pressure. They're getting buried more and more and more, so there's a lot more pressure. But the more pressure you have, okay, if you will, rub your hands together very lightly, and you don't notice a lot. Now press them together and rub them, and what do you notice? Heat. So the more pressure there is, the deeper it goes, the more heat is produced. Not just that, and we'll study this in the next chapter or two, not only that, but you got heat from inside the Earth coming up, like the volcanic material and stuff. So things get hot down there, okay? So you got heat and pressure, and then the other thing is hot solutions. Have any of you ever been to Yellowstone National Park out in Wyoming and part of Montana a little bit? Please, if there's any way you can wangle a way to do it, sometime during your life, go to Yellowstone. It is just about the most incredible piece of earth I think you can visit. What is it known for? Okay, actually it was, Lake Yellowstone was formed by a volcano, okay? And that is influencing everything else going on there. In fact, that had to have been one massive volcano because that Lake Yellowstone is one huge lake. And if that's all in the crater of a volcano, that was a major volcano, okay? But it's no longer active, and hopefully it won't be active during our lifetimes. Otherwise, it's going to be pretty dramatic, I think, if anything were to happen there. But there were enough fractures and breaking apart of rock material there that there's all sorts of ways that things are happening. Sort of like a volcano, but not quite. What is Yellowstone most famous for? Yeah, if they were old men, you'd call them geezers. But they actually call them geysers. Okay, they're not old men; they're geysers. And Old Faithful is the one that goes just about every hour. It's more really like 52 minutes or something like that. And not always, but very, very frequently. Okay? So all those geysers, not just geysers, they have sulfury emissions coming out of the earth. You've got unstable ground. You have what they call paint pots. I mean, it's a big area, and it takes a while to see, but you can drive all over that place and just see more and more incredible things. There is no collection of that kind of geologic wonders anywhere else on the earth that compares to Yellowstone. There is something in Russia, I think it's in Russia, or Soviet Union, former Soviet Union, somewhere, that may have a third or a quarter of what they had in Yellowstone in one general location. Nowhere else is there anything like it. It's just incredible. Okay? There are some parts that are steaming hot stuff just about all year long. It can be frozen snow everywhere else, and you have steaming hot water coming up here. So it's pretty incredible. And you get to see bison, you get to see all sorts of stuff when you go there. Try to sometime in your lifetime. Put it in your bucket list. Try to get out there to see it at least once. Okay? So, those are examples of hot solutions. That stuff bubbling up all the time, and that's changing the rock, I'm sure, somewhere in there some ways. So usually that's not as big as these two. All right. Now these causes are associated with geological events. When the crust moves, things get ground around, heat is produced, pressure produced. That causes the heat and pressure. Heating in hot solutions from magma intrusions, and that's what happens with volcanoes, or where there were volcanoes. That's what's happening in the big island of Hawaii right now. Kilauea is just going crazy out there. Mostly magma intrusion, not so much hot solutions. But if there's any water getting down there, that's now become hot solutions. Now, the temperatures must be high enough to cause recrystallization, but not melting. And that's the fine line that you have with metamorphic rock. You have to have enough heat to recrystallize the rock. That's why it's metamorphosized. It's changed. The crystal's nature is changed. Okay? But not hot enough to remelt it. Okay? And when it does remelt, then it becomes igneous again. Okay? So here is the sample of this. Shale, I don't know if you remember, that was a sedimentary rock. It shows up in layers, very much in layers. Okay? Well, that gets metamorphosized, and by the way, the layers are because there's deposits, then another deposit, then another. Everything's in layers. Lithification does occur, compaction and cementation, so it becomes a rock. But then more heat, it gets deeper, pushed down deeper and deeper, more depositions on top. This is highest, right? All right. More depositions on top, more heat, more pressure, and after a while, it changes the crystal structure of what was just sedimentary rock. Now it becomes slate. Okay? Now, slate, again, is very well known for the flat layers. In fact, what is one major use for slate? There's several, but what would be one?
Use for slate?
Second? Yes, slate.
Countertops for slate, no?
Actually, they probably could. I don't know if they do that much. That's usually granite and stuff they use for countertop. But some old buildings, like our church, the old part of the church, has slate roof because it comes in sheets. Okay? A lot of the buildings in New Orleans, I think, have slate roofs because they had a really big fire down there, probably the 1800s or so, and burned so many of the buildings, and something started in the roofs, and that's what led it. Ever since then, I don't know if they required people to use slate, but, or some non-flammable thing, but so many of the roofs in the older buildings that exist down there are slate. And you'll see that in other places as well. Now that's not tile roof, it's slate. Okay? Well, if you keep adding pressure and adding heat and adding more time goes along, it can actually change the crystal structure again and become what they call schist. Okay? A hard word to say. But if you have even more pressure and more heat and more changes, it becomes, and this is pronounced nice rock. No, G-N-E-I-S-S, nice. Okay? Now, do you remember a picture of a rock, and I think we'll see it again, that you could see layers in it, but they were all mangled and crooked and stuff, and it was up on the pedestal, had bright white lines that did like this in dark places early in the chapter. That was nice. Okay? All that additional heat and pressure has not only recrystallized, but also bent and folded the crystal up. So it's no longer in the layers that the slate, the schist is beginning to get out of that layer too. Now, does something look a little weird here at the bottom? What rock is that? Granite. Now, how do we classify granite rock? It's not metamorphic. It's igneous. What has happened? You add more heat, more pressure, more heat, more pressure, more heat. Suddenly, or at some point, it actually melts. And when it melts, then it recrystallizes. Once it's melted, it's igneous again. Okay? So, what started, all rock was one time igneous rock. The shale was pieces of that deposited and became sedimentary rock. More heat and more pressure changed it to slate. More heat and more pressure changed it to schist. More heat and more pressure gnarled it up into gneiss. And more heat melted it. And it became granite. Back to being igneous rock again. Okay, let's go to another. And that was, by the way, shale was a clastic sedimentary rock made out of pieces of other rock. Okay? Now, limestone, on the other hand, is also sedimentary. But that's chemical sedimentary rock because it was dissolved materials that came back out of solution and formed sedimentary rock that way. That was limestone. But that limestone gets buried under more and more layers, and now more heat, more pressure, limestone metamorphosizes to marble. Frankly, I don't know if you've ever dealt with marble rock. It is beautiful. In my mind, it's the prettiest rock out there. And we'll show you some examples of it. Limestone is fairly soft. I'm not sure you can scratch it with your finger, but it comes close. I know with a nail you can scratch it and mar it. Marble is hard as rock. Okay, the crystal structure has changed from the quartzite and other materials that were sort of loosely tied together in limestone. It's actually the heat and the temperature has changed. Now, you keep adding heat and pressure, and now it melts and comes back as calcite, which is igneous rock again. Okay? So once it melts and then re-solidifies, it goes back to being, that's a mineral calcite. Okay, sandstone. Okay? Sandstone, sand being mostly quartzy type material, silicon dioxide. It's where small particles of sand basically have been deposited, and then compaction and compression has trained it into sedimentary, classic sedimentary sandstone. But keep adding heat and pressure and heat and pressure, and now that the pieces of sand that were just sort of stuck together, glued together, now they're fused together, and that's called quartzite. Okay? and that is much harder. You can't break it off nearly as easy as you can sandstone. I'll show you some sandstone today. Don't think we have any quartzite. But that's now metamorphic rock. You keep adding heat and pressure to that, and what happens ultimately? You melt it. And once it melts and comes back again, resolidifies, now it's quartz. Quartz is igneous again. So you see everything, if it keeps getting more heat and stuff, it ultimately is going to melt and come back as igneous rock. All right, let's go to igneous fine grain rock. Now this could be the salt, that's fine grain. There are other fine grain igneous rock. Now this is a igneous. This is not sedimentary. These others have been sedimentary. Igneous rock, fine grain igneous rock. It gets buried, more buried, and more buried, and it gets heat and pressure, forcing those crystals together, fusing them together into new material. It can become a schist too. This wasn't sedimentary rock, it wasn't slate, it wasn't shale, slate. It was igneous, fine grained igneous rock. It became schist, and then with more pressure it becomes gneiss, and then with more pressure melts, becomes granite, which goes back to being igneous rock. So it changed from igneous to one type of metamorphic to another type of metamorphic, and then if it keeps getting too hot, it will ultimately melt and come back to granite. Granite is not fine grained, it's coarse grained. Of course, this is now happening deep in the earth. When it melts again, and unless it comes up as lava or something, it's going to be granite. Coarse, large crystal size, slow cool granite rock. Okay. Make sense? All right. That is your metamorphic rock. Now, here's how we classify the metamorphic rocks. First is, are they foliated or not? Now, what do we mean by foliated? I don't know if some of you ladies go through a process they call exfoliation. Okay, that's what it makes your skin. But what you're doing is taking off broken layers and incomplete layers of skin. So basically, you're taking off sheets. Okay, foliation means to have in sheets. Okay, any of you in your majors do a portfolio? You've probably heard of that. That's when you gather together the different sheets of demonstrations of your byproduct of your products. Okay, that's foliation. Things in sheets, alignments of flat crystal flakes into sheets. Remember, we said the shale was in sheets, the slate was in sheets, the schist a little less so in sheets. Your clay minerals quite often are in sheets. Various things will come. Your micas are definitely in sheets. So foliation, that's one way we classify metamorphic rock. How well are they layered? If they are, they're well foliated. Now this is caused by pressure on the parent rocks. Okay? Now some of that pressure could be fusing the sheets together, others could be keeping them apart. The rock cleaves along the plane between the aligned grains, and that's what your slate is. Slate roofs, because they've come off in definite sheets. So, non-foliated, the parent rocks consist mainly of one mineral. The grains are not aligned into sheets, and this would be a bit more like your gneiss. The gneiss have sheets, but they're really mixed up and folded over and stuff. That would be more of that. Your marble is not aligned in sheets. Those are blocks, okay? And marble would be primarily calcite, okay? Mainly one mineral, okay? So they're either foliated or non-foliated. But when they are foliated, there are several classes of foliation, okay? For instance, non-foliated would be quartzite and marble. Quartzite came from sandstone. non-foliated, not in sheets. Very finely foliated was that slate that you use for roof, very distinctly foliated. Finely foliated would be schist, and I would say gneiss was not foliated, but actually it's very coarsely foliated, gneiss. And then the next level of not being foliated would be non-foliated, which is quartzite and marble. So within the foliation, you have very fine, finely, and coarsely foliated, and then non-foliated with everything else. So that's another way to classify metamorphic rock. Either foliated or not, and if it is foliated, it's very finely, or coarsely foliated. Okay. Here's that same thing we just saw. Increasing metamorphic change occurs with increasing temperatures, increasing pressures. If the melting point is reached, though, the change is no longer metamorphic. Igneous rocks are formed because it actually melts and then decreases. Now, here is raw marble. If you had seen a similar piece of sandstone, it's really kind of dull, okay? I'm not sandstone, limestone. Sort of dull, kind of whitish in color like this, but really dull, and something you can mess with, okay? But marble, coarse grain, okay? Metamorphic rock, interlocking calcite crystals. These bright-looking crystals you see are basically calcite crystals. They are interlocked because they've been fused together by all that heat and pressure. Calcite crystals were recrystallized from limestone during metamorphism and formed bigger crystal size. Here's that picture I was talking about. This is nice rock. This is either here or that. This is probably from here, because you can see the layer. These wouldn't necessarily have layers. These would. So this is that nice. This banded metamorphic rock, very, very, very old, has at an age of about 1.8 billion years. That's way back there, folks. I mean, this is, not early in the Earth's life, but much earlier than we are now. It's probably among the oldest rocks on the surface of the Earth. And you can tell how much pressure and heat had to have happened to take those nicely foliated, finely foliated materials up here and twist and bend. That's a lot of pressure to do that to that rock. Because this was a layer, say maybe of one kind, that was layers of other kinds. So this is definitely at one time foliated. Now it's very coarsely foliated. Okay. Make sense? Okay. Now, before we move on, there is a person behind the science here, Victor Moritz Goldschmidt. Okay? He lived, he was living in the late 1800s, late 19th century, but he did all of his work in the early 20th century. He was a Swiss-born Norwegian chemist who has been called the founder of modern geochemistry. So you can read this about him. Very interesting. This cannot be your source for a paper. If you choose to write on Goldschmidt, you can't use this as your source. You can give this as your source of your ideas, but you have to go find the material from another source. They do mention some other things like X-ray crystallography, which I actually used in some of my research on my master's level. And that was developed by William and Lawrence Bragg after Max von Laue's original discovery in 1912. So you could actually write on either one of those, either one of the three of those. It's interesting at Göttingen, which is a university town in Germany. He, it mentions some other things there too. All right, so I'll just leave it like that. One of the reasons to pause and do that advertisement, remember a paper is due in this class, and let's see, 0 papers have been turned in. In fact, this whole term, this whole summer, we're almost at midterm, folks. We're within a week of midterm. In this whole term, I have received 2 papers is all. So please, folks, don't forget about your papers. All right. So I think I beat that to death. The last topic here is the rock cycle. Now, your book has some other really pretty pictures in it too. Your figure 1720 is that same banded metamorphic rock, very old. That's the same piece of rock we were looking at here, only a much closer shot of the surface of it. There was also a sample of marble, and I meant to bring in one that I think is marble that we found in our yard, and I don't know where it came from because there's no other. I forgot to bring it, but it looks a lot like this one in your book. But now we're ready for the rock cycle. And basically the last few slides and several things I've been talking about, the whole chapter compiles into this. What do we think of when we think of cycle? Second? Different stages. Okay, very good. If this was not a Y but an I, what is that almost spelling? Circle. Okay, the circle of life. I'm not going to sing whatever that is. Lion King, exactly. Okay, but that's an example of a cycle. Rocks live in cycles. Rocks are transformed into new types by the Earth's interior and exterior dynamical processes. The Earth is always changing. Slowly, but changing. Out in Hawaii right now, it's going pretty fast, okay? But always changing. You have moving continents, and when these continents are moving, there are places where they're grinding together, and that's creating change. Places where they're spreading apart, new stuff is coming up. They're always changing. Dynamical process, interior and exterior. We may not see some of those changes that are happening way deep, but this is what? Seas advance and seas retreat. When we were out in, what was it? I think it was last summer. Last summer my wife had professional meetings out in Salt Lake City, or near Salt Lake City, Park City, Utah. And it was right at a time in between terms, so I got to go with her. And because I got to go with her, she took a little extra time, and we went to Yellowstone again. We just couldn't resist that, and Jackson Hole, Wyoming, Tetons. But we also drove through portions of Montana and a little bit of Idaho and Wyoming, several different areas. And there was one place we ran into, and they were called the basalts. I've seen them on maps before, but I'd never been there. Now, how are basalts formed? Volcanic eruptions underneath the water. And here they were up here in, not quite in the Rocky Mountains, but awfully close. The Earth is always changing. At one time, that had been a seabed. And uplift has occurred, we'll talk about this in later chapters, had occurred, and now they're up way high in a hyper area. Those same basalts that were at the bottom of the ocean. Okay? I mentioned Salt Lake. Salt Lake is a salt lake because at one time it was part of the ocean. But it's way interior now, but it was trapped there by another. We saw a river there. We crossed, I don't think it was a Snake River, but it was some river there that some naturally occurring dam had broken. And water from the biggest sea probably on the face of the earth at that time went rushing down and dug out, and literally the walls, the banks of this river were vertical, almost vertical. I mean, they went down 10, 15 stories, just straight down. I said, how in the world would these form? We got to the thing and told about that lake. Can't think of the name of it now. But at one time it had been there, a huge lake, and its naturally occurring dam broke, and that water was rushing out and dug out that riverbed. Vertical. Okay. So things are always changing. We have also, in addition to things being built up, things are being worn down. The Appalachian Mountains at one time were probably the tallest mountains in the world. Now they're not even close because they've been worn down over the centuries. Okay? Whereas other mountains like the Rockies and the Himalayas, the Alps, they're still growing because, and we'll talk about those in other chapters. So you have things building and some things weathering and eroding away. Wind, rain, all sorts of things do that. This is one of the neatest little diagrams. All rock were at one time igneous rock. Okay? Now, where did igneous rock come from? Magma. The magma cooled, solidified. If it cooled slowly, it made coarse-grained igneous rock. If it cooled rapidly, it made fine-grained igneous rock. But they made igneous rock. It came from molten magma. Ignite, hot. Now, that igneous rock gets worn away, okay? And that worn away, the pieces of that fall out as sediments, forming sedimentary rock, okay? Now, how does that form? The process we call lithification. What are the two steps in lithification? Compaction and cementation. Exactly. Okay, so igneous rock break down, they get weathered and become sedimentary. Become sediments first, and then lithification produces sedimentary rock. But not all igneous rock goes through that. Some of them may get buried deeper and deeper. More heat, more pressure. What happens to the igneous rock? It changes. The crystal structure changes. That heat, that pressure, and now it becomes metamorphic rock. Okay? Well, okay. If more heat and more pressure happen, then that metamorphic rock can metamorphosize a time or two again, but at some point, too much heat, it melts, becomes magma, becomes igneous rock again. Okay? All right. That sedimentary rock we have. Sedimentary rock sometimes is not really well formed. It's not super hard. So it's really easy for it to weather away. By rain, by wind, by wear, by tear, by whatever, and it becomes sediment again, and it starts its own little cycle here. Or that sedimentary rock can get buried deeper and deeper, more heat, more pressure, and gets more metamorphosized also, and form metamorphic rock. That metamorphic rock can get broken into pieces and go back and become sediments again. Or it can get more heat, more pressure, and ultimately melt and become igneous rock again. So this is your rock cycle. It never stops. Sometimes takes centuries or millennia to happen, but it's always happening. The circle might go like this. It might go like this. It might go like this. It can go all sorts of ways, but that's the rock cycle. Always changing. Very, very slowly, but always, always changing. That's it for the chapter, folks. We're through with chapter 17. Guess what words I'm going to say next? Nothing replaces reading the chapters. So please, if you should have read it before I ever started talking about it, but if you haven't, go back and read it. Okay? Once you've read it, maybe a time or two, go check the summary out. Now this summary may be a little shorter than some. The key terms, maybe a few fewer than some. They're listed alphabetically, but they're given the page number where they're first defined or described. And then probably the best thing to use to study for your test are the applying the concepts. Okay? Only 43 here, again, a bit fewer than normal, but way more than you have on your test. Not the same questions. They won't be the same questions, but they'll be covering the same material. So if you got those down pretty well, you're probably going to do quite well on the test. The answers are given here. If you can't get the answer that they got here and don't know why, can't go back and read and figure out why, ask me, and we'll figure it out. They may have a wrong answer, or it may be you're not quite reading it right. Okay, questions for thought. I'd say this is a few more than normal. 19 questions for thought here. Again, think through these. If you can answer these, look it up in the book, whatever. For further analysis, we only got 4. That's probably fewer than normal. Invitation to inquiry. You can look at that if you want to. I don't think that's that beneficial, but you can look at it. And then the parallel exercises. If you got the big books, I know the answers are in the back. I don't know if in the thin books if they have those or not. I asked them to put them in, but I haven't seen them yet. Okay? Those are not probably as important, but again, that might give you more information. Okay. Any questions? Chapter 17. The lab will be starting in about 20 minutes, and the test will be the last 30 minutes of Tuesday's class. All right, so let's end the slideshow there, and let's us get started in Chapter 18. All right. Now, today's lab will be pretty closely related to what that chapter was. Most of the labs from here on, especially the geology portions, 18, 19, 20, and 21. No, 18, 19, and 20. They're going to be sort of covering everything we did. They won't be specific to a chapter, but they can, and we're associated with it. Because it's sort of hard to do a lab on plate tectonics since it takes a long time for that to happen, and you can't really do it. So we'll be covering other issues on the labs. Okay? Most of them will be, I think you find fairly fun. A few of them may be a bit tedious. This may be one that's a little more tedious. We'll see. So let's start from the current slide. And that is plate tectonics. What does this mean, or what do you think this means? Say again? Okay, the shifting of plates. That the Earth's crust, and a little bit deeper too, is made up of not one solid shell, but a series of plates that sort of hang together in different ways. So that's what we're going to be talking about in this chapter. We've already been talking about it when I mentioned Yellowstone, when I mentioned spreading and colliding and stuff. It's all plate tectonics. Here's the core concept. Earth has an internal structure, and here's that word again, cycles materials between the surface and the interior. It's basically almost talking about the rock cycle again, but not just the rock cycle. Okay? Now we'll see this slide toward the end again, a little bit more blown up. And we'll talk about this in a little more detail. These are the major plates. Of course, this takes the globe, which is a sphere, and flattens it out, so this isn't exactly dimensioned correctly. But we live in the North American plate. But the North American plate covers a lot more than North America. It also covers half of the Atlantic Ocean, okay? North Atlantic anyway. Greenland. Much of stuff is in it here. Okay? The Pacific plate out here is huge. It covers the Pacific is huge. It covers large portions of the Pacific, but not all. There's another plate here, a smaller plate called the Nazca Plate. It's in between the Pacific Plate and the South American Plate. We'll talk about this more in detail. There's a Caribbean Plate here. It's its own little plate. There is a tiny little plate up here called the Juan de Fuca Plate. I mean, it's so small, yet a lot of activity goes along with that. Okay? You have the Eurasian Plate. It's Europe and Asia. It starts in Europe. Well, it starts midway through the Atlantic. It's all of Europe, Spain, Britain, all that, all of Europe, and much of Asia. Okay? Now, there's another little plate in here, fairly good size, the Philippine plate, which most of the Filipino islands are on, plus some other stuff. There's the, as I mentioned, the South African plate. There's a plate here they don't even give a name. Oh, I'm sorry. No, they don't give a name to it. I thought it was part of the Antarctic plate, but that's the blue down here. They don't list that. I don't know what it is. Here is the African plate. Now, the African plate is about half of the South Atlantic Ocean, all or most of Africa, not all of it, and goes out into the Indian Ocean. There's an Arabian plate, which is mostly Saudi Arabia and the other countries that are on that peninsula there. Okay. Then there's the India-Australian plate. Who would have thought that those were on together? Not part of the Eurasian plate, but these are together. Most of that is under the Indian Ocean and some of the Pacific, but the country of India and Australia are all part of it. So we'll get to see this later and talk about especially the boundaries. But that happens because of the Earth's internal structure and the fact that it cycling materials mostly around the boundaries of the plates. Okay? Now, here's Lauren. And by the way, for those who did come in a little bit later, I did pass out to you your second test. The last person to take it took it last Tuesday. I got it graded, so I can return those to you. We're still missing one lab 2. She hasn't been here in a few days, like 3 days. Today would be the 3rd day she's been absent. So I don't know what's going on with her. She was removed from the role, but then put back into the role. So I don't know what's going on there. If I find out she's not going to be here, then I can return lab 2 to you as well. So that's the only one we're missing. Lab 3 you all have working on, right? I know the moon's up in the evening now because I see it when I put the dog out. So I hope you're doing your measurements. Now, if you're the early morning person, you may have to wait a little longer to get it done. Test 3, which most of you took last Tuesday. 3 of you still haven't taken that, so she's one of them, by the way. You might want to get those done as soon as you can. And in about 15 minutes, we'll be starting the chapter 17 lab, and we'll have the chapter 17 test on Tuesday, the last 30 minutes. Okay, so history of the Earth's interior. Okay, we think the Earth was formed about 4.6 billion years ago. Okay, the Sun was formed about 5 billion, maybe 5 point something. So the Earth formed a little bit later when the solar nebula, that cloud of stuff from all the activity of the sun blowing up and doing all this kind of stuff, sending out material. Finally, the Earth formed about 4.6 billion years ago. Probably most of the solar system about that time. The early Earth was so hot, and from this, the solar nebula, the blowing up, when the fusion started on the sun and it blew up and sent stuff flying and then sucked it back in and all this kind of stuff. Everything was pretty hot then, really hot. So Earth had a melted surface, and it was also getting bombarded with lots of other materials. So it kept it hot for quite a while. But after a while, the surface did cool and began to solidify. Okay? crystallized. All those rocks were igneous rock. That's why they say all rocks were one time igneous rock. Because they all came from molten material. Every bit of it. So all the rocks were igneous rock. But then the processes of deterioration and also pressure and metamorphosis, all that kind of stuff started happening, and you started forming other rocks. That was last chapter, the rock cycle. Now, the heat accumulated from the radioactive decay, remember? All this started from this fusion that's happening on the sun, and actually there was still radioactive decay materials from whatever star had blown up to form that gas that the sun came from. So there was lots of radioactive material out there. That led to a second melting. This time it's of the interior. Okay? Heat accumulated. See, especially once the surface had cooled, now heat wasn't escaping as fast. So now it accumulated on the inside. So you had the interior melting. Okay? The melting occurred in pockets, but not throughout the interior. There was some interior that stayed solid, and some where there was maybe more heat, more pressure, more something, it was melted, so it's in pockets. So what we had happening was something they called differentiation. Okay? Sometimes get too far from a microphone, but I like to be on that side when I'm doing it, but I'll try to stay over here where well, I'm talking away from it. Maybe if I project back, it'll be good. Okay, differentiation. You have melting, which when that happens, gravitational settling of the heavier materials, okay, like uranium, iron, the heavy stuff settled out, okay? Now, the lighter stuff made its way to the surface. That's why 92% of the crust of the earth is made out of the silicates, the light stuff. Okay, now some of the ferromagnesium silicates are a little heavier, but most of it's the lighter stuff. And we'll see this later too, the continental crust was really light. Okay, that's the granites. The salts are heavier in iron, so they're under the edges. So you'll see, we'll talk about all this. It gave the earth its present stratified structure. Okay? Well, we're going to talk about that in a minute, so I won't go into more detail then. The outer core of the earth, now this is way, way deep. The outer core is still molten, still melted. Mostly iron, not totally iron. Now that's technically probably not where our volcanic material comes from. That comes from these pockets that occur up in the upper part. Some of it could come from down there, but I would think most of it didn't. And maybe it's moving into the pockets. I don't know. We had a really big Earth, so we have to figure it out. So, what's happening at the Earth's center? The pressure there is about 3.5 billion atmospheres. Okay. Now, we have over us 1 atmosphere of pressure. Okay. Now, in terms of numbers we're probably more used to, it's about 14.7 pounds per square inch, PSI. Okay? That makes sense to you? That when you blow up your car tires, okay, you are, what is that, usually about 40 to 60? Yeah, is what pressure you put in there. That's PSI, pounds per square inch. On us right now, 1 atmosphere of pressure, 14.7 PSI, almost 15 PSI, pounds per inch. 15 pounds. Okay, 15 pounds would probably be, demonstration, it's a fair amount of weight, right? Now, what's a square inch? A square inch is about your 2 thumb joints together like that. 1 inch this way, 1 inch that way. This is about 1 inch, and so that would be about a square inch. So think of how many square inches are on your body, for instance. It's a lot. And 15 pounds on every square inch of your body. It's a lot of weight. Why don't we get crushed? Because we got more than 15 pounds pushing out of our body. You have blood pressure, you have body in, the less flows out because you have more weight, more pressure inside you than is out. So that's right. Now, my mom used to do this. She's dead now. But she would take her hand and say, "Look at this." She would pick up the skin on her hand, and it would make a peak. Okay, I'm beginning to make a little peak. It goes down really slowly, sadly. But if you did it, your probably goes right down. Right? That's because as you get older, your pressure is a little bit less. My mother called it Turner pressure. She was an RN, so she had a name for it. Hers was standing up for quite a while. Okay, but anyway, that's 1 atmosphere of pressure, 14.7 pounds per square inch. So that's a fair amount of pressure. You go down 10 meters in the water, okay? Now, 10 meters, I'm about 2 meters tall, about another meter above me, so each floor is about 3 meters. So a 3-story building would be about 10 meters. So that's the main part. That part of this building, where there's 3 floors. So go outside and look from the ground up. That's 10 meters. If that was 10 meters of water, that's another atmosphere of pressure. Okay. So then you'd have to know 10 more meters, and that'd be another atmosphere. 10 more meters, another atmosphere. Think of how many of this it would take to get 3.5 million atmospheres. That is a lot of pressure. A whole lot of pressure. That's at the Earth's center. Temperatures down there, 6,000 degrees Celsius. That's hot. Now here's the strange thing. Even though it's that hot down there, all that pressure keeps it a solid. The outer core has a little bit less pressure, not nearly as high a temperature. There it becomes molten. So at the very center, solid, the outer core liquid, and then you get solid material outside that. Okay, we'll see pictures of that very soon. Okay? Now, what are evidence? How do we know this? Has anyone taken a core to the center of the Earth and found all this? No way. Our biggest drilling operations ever barely go through the crust. And the crust is a narrow little strip, just no more than a mile or 2 deep. Okay? So no, we don't know this from taking core samples, certainly not. But the fact that we have a magnetic field, now that sounds strange. Why would that indicate that we have that internal structure? Because let me tell you what makes a magnet. Moving charge. So why would we have any moving charge? Why does that indicate we have structure in the Earth? Well, remember what I said, the outer core is liquid, molten material, and above that is solid, and the Earth is spinning. Well, the solid stuff has to go with the Earth, right? It doesn't have any choice. The liquid can slosh around in there and doesn't have to spin as fast. So when those are hitting, and that's not a smooth interface, probably jagged, different kinds of rock and stuff flipping out and stuff. When that spins like that, it knocks electrons off. When it knocks electrons off, they spin too. Moving charge induces a magnetic field. And because it's going in a circle, the good old right-hand rule, if the charges are going this way, you have a pole going that way. So you have the North Pole and the South Pole. Okay? Now, other evidence, gravity effects. Okay? We can measure the density of the Earth's materials that we have at our disposal. And we know the circumference of the Earth. We know the diameter of the Earth. We know lots of things about it. If all the Earth material were the density that we have on the surface, we wouldn't have as much gravity as we have. That means it's getting denser as you go down, which makes sense. If it's going denser as you go down, you have different striations. Yes, you have different structure down there. Very different structure as you go. And the gravity effects show that. Heat flow. Okay? Heat is transmitted through solids. That's what's called heat flow. And through liquids and gases too. And by measuring how that heat transmits or is transmitted through the earth, we have other examples of the Earth's internal structure. And these are the big ones. I mean, these are pretty big too. The vibrations of the earth. What do we call those? Vibrations of the earth? Earthquakes, exactly. Okay? Now, every earthquake that happens, you have seismic waves. There are 3 types of seismic waves. And we'll talk about these a little later, so I won't go into great detail now. And because those 3 types of waves travel through different materials differently, we can see by the actions of that and the evidence from that there's different structures going on there. We'll talk about that more in detail. They also travel at different speeds. And so by measuring the difference in the speeds, you can tell something. These radiate outward from the earthquakes, and here's the other thing. Because of earthquakes, we have a great system, international system, set up for monitoring earthquaking material, okay? And because nuclear reactions, nuclear explosions, are sometimes almost as big as earthquakes, we can tell when someone set off a nuclear reaction by our seismic stuff. So nobody can sneak in a nuclear reaction. Someone's going to detect it and say, hey, that didn't have the characteristics of an earthquake. Pakistan just, so some countries, you can run, but you can't hide. Okay. Now, unfortunately, we've run out of time. Let's see if there's anything I may have missed as I was going. It shows here a picture of a naval vessel or a drilling ship that is drilling deep into the ocean floor, but still you're barely staying in the upper part of the crust of the earth, barely scratching the surface, no matter how deep you think you're going. And we've been talking about the Earth's internal structure. We will start next time with seismic waves, which is where we started last time. So last time I taught the course, that was my mark there. So we'll begin there next time. And I will shut this down. If y'all need to take a very quick little break, we will be forming up, and I'll have to check and make sure it's still open. 256 is where we'll go. You want me to go on and give you the lab? So let me go on and do that now. And you can head down there, but don't start messing around with much until I get there. I've got to shut down a few things and stuff now. I'll continue recording with my computer, but there won't be any projector. Well, they have a projector down there. If I find I need to, I can connect to that and project. I don't think I'll need much. Okay. Take one and pass 2. There you go, and pass 3. Okay. One by yourself. Okay. That's one. That's right. What's that? You can't use that as your only resource. You have to go to yes. Say this again. No. We'll talk about that too. That is, in fact, I think they have it in here as a mistake and misunderstanding. Okay. So, if you want to take a quick break, do so. No more than 10 minutes, but take what you can. We'll cover this next time, so you don't have to get this. That's where we begin next time. I wanted to get to the slide so it'll pop up correctly. So I'm going to... Okay, you have before you the lab, Properties of Common Materials, Minerals, okay? Just a few things. The fundamental building blocks of rocks are minerals, okay? Naturally occurring, inorganic, solid elements or chemical compounds with crystalline structure, just like the book show, okay? Now, I have some boxes that show some of these minerals. However, to get all the stuff that you really need, much more efficient to do it online. Go to a database. Now, where I'm going to send you will have some, but not all. Okay? And I'll explain that in just a minute. So what you'll need to do is, if you can log in there and do, go to your URL and type in webmineral.com. WEBMINERAL, Web Mineral, written as one word, Web Mineral. Don't put an S on it. Webmineral.com. Okay. Do most of you, all of you, get something to come up there? All right. Now, actually, I probably should have given you one more part. If you can go back to that top and put slash, and I think the first one listed here is calcite. Yeah, CALCITE. So, webmineral.com/calcite. And you should get something about calcite that comes up. CALCITE. Okay. Everybody get something? What's that? I'm sorry.
It said that when we added the slash around it, it said that page was not found and it's sent back to the original page.
Okay. All right. Well, then most of you are on that home page, right? You see those 4 pictures? Okay. So what you do is scroll down. Okay. You see where it says alphabetic listing? Okay. Click on that. Okay. And scroll down. I think they've changed the website slightly. On the alphabetic listing, click on the C. Hot, that's it. Okay? You see you get a whole bunch of C's there. Okay? Scroll down there until you see calcite. CALCITE. Further than I thought it would be. There it is. Okay? And then click on calcite. And then what we're looking for is physical properties. So we scroll down here. Physical properties of calcite. See it? Okay? And that's just about everything you're going to need to know right there for calcite. All right. So, sorry, I probably wasn't so people at home could hear that. But go to webmineral.com, and then when you see that alphabetical listing, click on the C for calcite. And then you can do your other minerals the same way. Now, here's what you'll be looking for. I want to point something out to you before I forget it. we're going to look under several properties. The first will be color, and you see color is one of the first things listed, right? Okay. Then streak. You see where that's listed? Okay. Then you'll see hardness, and may have several ways to express that. And then I think cleavage and fracture are on one line. Cleavage/fracture. There'll be two lines on your website, but you'll need in your lab, you put them all in one block. Okay? Then you have luster. Now this isn't in the same order. In fact, on the table it's color, then luster, then streak, and so on. Cleavage, fracture are together. Now, density. You don't see, if you turn to pages 332 and 333, you don't have one there for density. That's what you put under other. So where you have the title other, put density. And I think you'll find that in the table. Okay? Now, when you finish filling out the table, that's page 332 and 333, don't forget to go back to page 331 and answer that question at the bottom of the page. Was the purpose of the lab accomplished? Why or why not? Okay? You can just write a little something there. Just write something. Whether you thought it was accomplished or not, write something. There's no right or wrong answer, except a blank is no answer. Okay, so write something there. So let's go back and look what you're filling out. Now, probably under color, you'll see a ton of colors. So just write the top few in that thing. You just don't have much room. You don't have to list everything they say. List the... What's that?
The initials, like Y, or blue.
Second?
Initials.
As in yellow or black? Is that what you mean? Well, be sure for black you put BL and brown for BR. You know, that I can tell. But just write a little bit. You don't have to write everything they have. Just write a few of the predominant colors. Luster is usually just one word. Okay? Streak is usually just one. Okay? Hardness, they may refer to it in a couple of ways. They may give a number, they may give a mineral, and they may give something else. So that would be hardness. Cleavage, fracture, there's two entries there, one for cleavage, one for fracture. So write a few words for cleavage and a few words for fracture. Now the cleavage may be given as a series of numbers, 101 or something like that. If they have it, put those numbers down. Fracture, if they have anything there, put whatever they have. So write a couple words for cleavage, then do a slash and a few words for fracture. And then the other column is density. All right. Now, let me warn you of this. Not every word, not every mineral that you see on this page will you find in that column. Most of them you will. There will be a couple, and I'm trying to remember which ones they are now. I believe probably limonite might be one. I'm almost certain feldspar is one. Bauxite, I think, is one. There are a few of them that when you type them in or you go to the alphabetic listing, you're not going to find them there. So here's what you do then. Maybe pull out of this table, or maybe you can get it here, and do a search somewhere on your computer for that word, bauxite or fluorite or whatever one you're looking for. And then you'll see a listing of other minerals. Jot those down, go back to this table and put one of those in. See, for instance, bauxite is an ore. I believe that's aluminum ore. That's not really a mineral, it's an ore. So go back to, type in bauxite, and then you'll get something like goethite or something like that, and that's the one that you'll find in the table. But when you do that, be sure you write that. Like if you can't find feldspar, look up feldspar, find another name for it, write that name that you can find in the table, and then give the information on that. Does that make sense? Is anyone listening? Okay. If you have any questions, please ask. Now, what I'm going to be doing while you're doing that is I'm going to go get some mineral samples, some rock samples, so you can look at some of these and you'll see some of the ones you're doing. For instance, I have some calcite crystals that you can see, and there'll be others too. So I'm going to put this on pause for right now, and I'll be back. Okay, the question was under chrysotile, the cleavage fracture didn't have its own category. What you can do is, again, y'all know how to do this. Google it. Say, what is the cleavage/fracture of chrysotile? And see if you can find that.
So if it says none, you want us to find it?
Okay, if it says under there none, now some of them do that. Let me see what you're talking about. What's that? Okay, cleavage says none, the fracture is concordant.
Yeah.
Okay. So put none/that. Okay. Now what? See, that's what I thought you had at first, but it's not. A few of them have no classification there, and you can either Google and see if you can find something, or if that doesn't work for you, if you have something like the crystallography or something like that, just put down a word or two that you see there, okay? That seems like it would be defining it. But try doing. Now, the second question was, what if it says none under cleavage? And some of them do say. Which one was that, by the way?
Hematite.
Say again? Hematite?
Yes.
Okay. Hematite, which is iron ore, it doesn't have much cleavage to it. So none is a perfectly legitimate thing, but then /fracture, because that's why it's cleavage fracture. Sometimes it'll cleave quite well and doesn't fracture much, or it'll not cleave well at all and fracture like crazy. So that's why they put them in one thing. So put whatever word you see, / and then another key word for the other part. Okay. Good questions. Now, I brought into the lab, or to the room here, a bunch of samples. Okay? And I'll be talking about those in a minute. And I'll try not to be too distracting, but I'll put them out. I'll scatter them around at different tables. Please take a look at them when you'd like to, and take a look and ask me questions about any of them. Some of them are labeled, some of them are not. So I'll put those out. I'll put this on pause for a minute more. All right, I'm going to do some talking here. Y'all can continue working. Just give you an idea. Up here in this first table here on this side, I have a couple of chunks of rock, but when you look at them, I think you'll see that they probably have large quantities of quartz mineral in them, quartz mineral. You can tell by the color to some extent. This is sort of pink quartz here, some white quartz, but the shape, you can almost see those large crystals of it. This smaller piece that's more white, you can definitely see those prisms of quartz when you look at certain angles of it. So this looks like pretty much both of those are good samples of quartz. Around that, here are 3 samples of granite, and we'll be using one of these samples later in another lab. This shows a typical white granite. Now, of course, there's some non-white material in it because it's a mixture of minerals. Remember, granite, but you see it's relatively large particle size or crystal size. This isn't super large, but it's larger than normal. Then here's a brown one. Now, when you look at the polished side, it looks a little different from the non-polished side, but you can still tell from where it broke that there's pretty large crystal sizes. And this one has a lot more brown and black in it than the white did. Now, this next one is called Verde Butterfly from Brazil. They call it a granite, and the polished side looks very dark for granite. But if you look at the other side, you see it's not nearly as dark as what it seems, but you can see large crystal size in these. So you see granite can have a variety of crystal sizes as well, and a variety of colors. Now this is getting a little bit dark for granite, but this is way on the one end of that scale. And where it broke, you can see the crystal and some of the cleavage, you might say, in there. So that's the first table up here. Let's go to the table here. And this is sandstone. Now, this is at least 3 samples. Now, this piece of sandstone, when you rub on it, you can feel the grittiness of the sand, but you don't break it off. Don't rub too hard on this one, because if you do, it starts coming out. Now, my guess is either This one didn't have the compression, the compaction, or the cementation, which or both, I don't know. This is very well compacted and cemented together. This one is not. You can rub those off. Here's another sample. Again, the feel of the texture of it, it's a pretty hard sandstone, just like the other one. Different colors, though, of course. Okay, moving on around to this table, I put 3 different mineral rocks here. There's 4 pieces, but 4 different ones. The first is the Indiana limestone. And if you just scrape on this, you see it's not that hard. I mean, it's hard, but it's not all that hard, and it seems like it has sort of large pore sizes in it. Then they have something called classic travertine from Turkey, and that seems to be some sort of an intergrade between the limestone and marble. It's not as hard as marble, but it's a lot harder than limestone. I think it's in that same family, but then these two are 2 pieces of limestone, of marble, and you see they're much, much harder, not much pore space in between the crystals. The crystals are bigger because that's metamorphosized. My guess, from limestone, which is a chemical sediment, travertine is somewhere down the scale of metamorphosis, and marble is at the end. The marble, you'll see, is quite heavy and quite dense feeling. Okay, now this table here, it's messy, and sorry about the mess, but these are samples of calcite. And some of these crystals are just phenomenal. They're almost individual crystals here, but some of the bigger pieces, if you look at those, you see beautiful size and shaped crystals, and you'll compare this to what you saw on your thing, and you'll see that these are calcite crystals. Now, what I didn't know, these were brought to me by a student in my class several years ago who was also a miner. He's a young kid, and he had worked in the coal mines, and he said, yeah, the calcite shows up next to coal quite often. So he brought me some chunks from the coal mine, okay? And these are just phenomenal samples of calcite. I tried to leave as much of the coal out of it. And since I was here with coal, I don't know if it was him or someone else, I think brought some other samples of coal that you'll see here. But because they're messy, I left those in the back. Those are calcite crystals. Going over to this table, there's 2 things on this one. The first one here is just a group of different rock, okay, of varying kinds. And I put this one here for an example. Remember, we said color is not always the most identifying thing. Now, this is a rock, not a crystal, a mineral. But you see, that looks pretty brown, right? But a piece broke off, and it's a very different color inside. So color is not the best discriminator, because depending on conditions, you might have the same piece of rock having different colors. Same thing happened with this one. This, I think, was probably sandstone, though it's a little less sandy feeling, so it may be mudstone, and it's one color on the outside, sort of a much brighter color on the inside. Again, that wasn't intentional, it just broke in process. And then there's some other samples here. I don't know exactly what they are. This, I'm pretty sure, is slate that we were talking about today. It's foliated in sheets, okay? This is usually called chert, which is another mineral. The odds are they're all silicates, because 92% of the rocks on the Earth's surface are silicates. But then I have this one that also has a break in it. Almost looks like an egg, doesn't it? But where it happened to break, I didn't break this on purpose, but it did. If I can get it apart now, you see there's something else going on inside. This is what they call a geode. There's something formed in the center, chemical reactions and stuff, and started separating out minerals in a certain way, and then they changed as further they got out. So it's different in the middle than it is on the edge, in the interior, and then different on the edge. That's a type of a geode. I love geodes. They're just so neat to look at and mess with. And that's what I have here. This was actually a purchased geode. I think my wife got it or someone gave it to us. And you see very different mineral in the center. And what they did, they took a rock like that and sliced it. That is the edge of it. And then look at the different colors in it. And this was another one. I had two that were somewhat similar. This is much darker blue. And that's a cross-section of a geode. Probably formed by differential settling of probably in liquid solution. Okay, so that's that one. And over here, I think this is the final pile. This is what I was talking about in my bathroom, what the tile man called black granite. And later my niece, I happened to talk with her last night on the phone. She said no such thing as black granite. Now when I taught the course, I think she's absolutely right. But what you'll notice is very fine grain mineral. Unlike the granite over here, which is coarse grain, this is probably basalt. Dark, dense, basically almost black. Where it's not polished, it's not as black, but you can still see it's very dark, very small grains. And there's a few samples of that. We'll be using that in another lab. So, feel free to go around, play with them. You'll probably have to wash your hands when you're through, because they are sort of dirty, okay? And let me plug my computer back in. Question? Okay. Okay. There's an example. That was one of the ones that you have multiples of. You pick whichever one you like, but write down, so you're picking which ferro hornblende? Is that the one you're picking, or magnesium hornblende? Ferro. Okay, write that down over the top and then give the description for that. Well, some of these you will have, you either can't find anything because it's too big a classification, then you have to Google it and find what minerals are in that, or you may see it on the screen here, and then you write down the information for that. All right? Let me go wash my hands again, and I'll be back in just a couple minutes. If you have any questions, feel free to ask. Any other questions? There we go. Did you get that one question?
Yes.
You did get that. Huh? Oh, yeah. Good, thank you. Okay. I thought you said Carl Rove, and I said, he's not been in the news in a long time. Okay. I got you. I forgot to turn off